Hello everyone, I'm Ali. Today I'm going to talk about a very general problem that we frequently encounter. We have a large k-mer set obtained from a genome collection, and we want to perform some sort of a search using those k-mers, but the limitation is the memory. We have way too many k-mers that we can fit in memory, so we have to select a subset. So this talk will be about selecting that subset of k-mers. In the context of metagenomics, we have a complex environmental sample, we sequence it, we end up with a bunch of reads. Then we can either try to assign a taxon ID to each of these reads, or we can try to estimate the overall taxonomic composition of the sample. Whatever we do, we have to find some similar reference genomes to these reads. One popular way to do that is that you can build a searchable index, for example, a hash table using k-mers, and then you can search similar genomes using these k-mers in a fast manner. But this is not an easy task because our databases are quite incomplete. We have millions of species. Even within each species, we have a huge biodiversity. So our databases will remain incomplete. And when you have incomplete databases, you will encounter novel sequences that will lack a close reference genome in our databases. So we have an example here, Kraken2, which is maybe the most popular tool out there. And its recall drops quite fast when novelty increases. And we quantify novelty here by the distance to the closest match to the closest reference genome. So there are two possible solutions we have. The first one is you can try to increase the sensitivity of your search. You can try to find more distant genome matches. And to this end, we recently developed Consult2. Consult2 uses locality sensitive hashing to control the Hamming distance of inexact k-mer matches. By controlling the Hamming distance and utilizing this additional distance information, Consult2 is the best k-mer-based tool in a popular benchmarking challenge, KME2. You have L1 norm on the x-axis, and Consult2 has the lowest L1 norm among k-mer-based tools right after Metaflan, which is a marker-based tool. And the next direction, which we will focus today, is enhancing your reference set. You can sequence more genomes, you can sequence more species. From each species, we can have more genomes to have a better representation of that species. But then the challenge is that you are limited to the subset that you can fit in memory. So we have to reflect this enhanced large databases in our selected subset that we can fit in memory. And for this purpose, we developed Crank, which I will describe. Today, Crank can select a representative subset of k-mers from a large collection of k-mers, and it uses the same classification algorithm as Consult2. And by just changing the selected subset, we improve performance of Consult2 quite a bit. And in addition to being able to improve the performance, we also reduce the memory usage down to 50 gigabytes from 140 gigabytes. So we have a smaller k-mer subset, which is more representative. And just changing the k-mer set allowed us to improve L1 norm error. So how can we do that? Before describing that, I want to state the problem a little bit more formally. We have a k-mer set limited by k here, a large set, and we have a limited budget m, which is the number of k-mers that we can fit in memory, and we are also given a taxonomy. So our goal is to select the subset from this large k-mer set so that this smaller subset represents the entire collection well, in the sense that we can perform high accuracy taxonomic classification. So what can you do to select k-mers? You can just simply randomly select k-mers. This is the absolute baseline. You can use minimizers to exploit the local redundancy that you have in your genome. There are overlapping k-mers. You can just select one among overlapping k-mers. But even minimizers, each genome will introduce some new k-mers because even given two pairs of genomes from the same species, they will share only a small portion of their genomes. And the other dimension that you can try to utilize is the evolutionary dimension. We know that some genomes are more similar to each other than others. So we have this redundancy in the evolutionary dimension. Some genomes are similar. So we want to try to exploit this dimension as well to have a better representation of the entire set. And for this, Crank utilizes the taxonomic tree itself. It's a hierarchical subsampling procedure. We have all our species and a taxonomic tree, and crank performs post-order traversal on this tree to hierarchically select some number of k-mers from each of these groups. So at least we have our species, we have k-mer sets for each species, and during the traversal at each internal node, crank basically combines k-mer sets of the children of the current node, and after combining, taking the union of k-mer sets, it removes some number of k-mers, filters some number of k-mers based on some criteria. The goal is to satisfy the size constraint that we have, the budget M, and at the end of this traversal, we have M many k-mers at the root in our index. But the question is, how many k-mers are we going to filter, and which k-mers are we going to select and keep in our index to satisfy this constraint? So the first question is, how many k-mers should we keep for each taxon? Baseline, you don't need to do anything. You can just wait until the end, and you can randomly select M k-mers from the global k-mer set. But the problem is that this will lead to proportional contribution by each taxon. The problem about proportional contribution is that we have sampling bias. Some species are far better represented than others. For example, for E. coli, you have thousands of species, and the final library would be dominated by such species, such groups, if we do proportional contribution. So what we do is we instead impose a size constraint for each taxon. And this size constraint, the goal of this size constraint is to remove k-mers from those bloated taxa, such as E. coli, earlier during the traversal, and we somewhat treat smaller taxa, less represented taxa, less aggressive, and we delay decision for smaller taxa to the later stages of the traversal. I will just skip these details in the interest of time, but just using this adaptive size constraint, this size constraint, instead of waiting until the end at the root, we could improve F1 score of our taxonomy classification quite a bit. We have this green line, which is selection with constraint, and the baseline is the orange line, and we have higher F1 score across all ranks. The other question is about ranking. Which k-mers should we keep? Which k-mers should be sampled from the entire collection to represent the collection well? Again, the baseline is random selection. You can just randomly remove k-mers until the size constraint is satisfied. One alternative is that you can keep discriminative k-mers. You can keep shared k-mers. You have k-mer sets for each species. Some k-mers are shared across species. Some k-mers are discriminative, specific to some species. So there are these alternatives that we have. But unfortunately, none of these alternatives could outperform the baseline random selection. So discriminative k-mers are quite worse than random k-mers. Shared k-mers are slightly better, but there is this extra computation introduced, so it may not be worth it. And we thought that in addition to keeping shared k-mers, since it performed better, we could try to consider one more aspect too, which is the coverage. You want to cover all groups, all taxonomy in a sufficient manner. So the intuition is that we want to keep shared k-mers, but we want to ensure no group is left uncovered. And here what we can do is, let's say during the traversal, we are at this parent taxon and it has 4 children, T1, T2, T3, and T4. And let's say T1 has way too many k-mers, surviving k-mers compared to T2, then we can afford to remove k-mers from T1, but we shouldn't remove k-mers from T2 because that guy could lose the entire representation. So that's the intuition here, and we have a scalable heuristic to sort of impose this intuition during the k-mer selection. And doing that, we could improve random baseline and shared k-mers using this coverage heuristic, the purple line. So that's even higher F1 score. And combining all these heuristics with some minor tricks in a scalable implementation, we had crank. So crank uses all these heuristics to smartly and select k-mers in a taxonomy-aware manner. And we simulated reads across different novelty ranks. So we have the blue line, which is crank, it's above the other tools. On the x-axis, we have memory. So for lower memory levels, crank is performing always better than other tools. And for Chemi2 challenge, again, we have crank, which uses far less memory than Consult2, almost 1/3 of the memory used by Consult2, and it has lower F1 norms across all ranks. And it took only 3 hours to build a library from the entire RefSec snapshot from 2019. So I think that's all. That's what I mentioned.